We will calculate the complex Fourier series of a periodic waveform. We start by calling up the complex Fourier series procedure, CFS standing for complex Fourier series. Now inside this procedure, we are going to enter the periodic waveform. Now this is a typical periodic waveform of period 4 from 0 to 4. That is your first half period. That is your second half period. Over the first half period between 0 and 2, we have the straight line 2 minus t. And over the second half period between 2 and 4, we have the straight line 1 plus of t. When we press KG13 steps, we will see the workout. Before we do that, just bring in the timer. There's the timer. Click on there, go up. There you can see the timer is activated. So let's press on here and see how the answer develops. The timer ticks, the light is on. When this light goes out, that means the calculation is done and the timer will of course stop. 8 seconds, 10 seconds, 12 seconds, 13, 22, 23. There, it has stopped. So we took 32 seconds on this laptop to calculate and sketch the complex Fourier series of this periodic waveform. There the light has gone out. What we have here in blue is just an explanation, a sort of a background, especially for those who are studying engineering. We explain the following. Any physical waveform W of t may be represented over the interval. Let's say the waveform exists over the interval between, let's say, a and a plus t naught. It can be represented as a complex Fourier series by this formula. There's your waveform, and this on the right side, we will say it's a complex Fourier series. N is a parameter going from minus to plus infinity. The n here is the index on this C here. Now, what is the Cn? That's the complex phasor Fourier coefficient Cn. And how do we calculate that? By means of this formula. We can also calculate C naught by this formula. When n is 0, that means this exponential will now be 1. And we can calculate C naught by this formula. We prefer to calculate C naught separately. Otherwise, if we do not use this formula, we will have to get C naught from here. That means we will have to use L'Hopital's rule and so on. The omega naught is given by this formula 2 pi f naught, and it is 1 or 2 pi over t naught. But now we go further in the explanation. If this W of t is periodic with period t naught, as we have here in our problem, then this Fourier series representation is valid over all time. Then we say that f naught is the fundamental frequency, and it is given as 1 over t naught, where t naught is then the period. And then the frequency nf naught is the nth harmonic frequency. The Fourier coefficient C naught, that is identified as the DC value of the waveform. And we know that Cn is in general a complex number. Some properties of the complex Fourier series are if the waveform is real, like this W of t is a real waveform. So if the waveform is real, then Cn is C minus n star. What this means, first note that n is an integer here in this Fourier series ranging from minus infinity to plus infinity, but it's an integer. So we have then positive integers for n, we have negative integers for n. So when we say that Cn is C minus n star, we mean that Cn over the positive integers is equal to the complex conjugate of Cn over the negative integers. That star is just complex conjugate. Number two, if W of t is real and even, the waveform can be even. That means W of t is W of minus t, then the imaginary part of Cn is 0. And if W of t is real and odd, that means if W of t is minus W of negative t, the real part of Cn is 0. So now we start with our workout. Here's our periodic waveform, and here we have sketched it. We go down. So this particular form here compares in general to this form over here, where we have two general straight lines. Let's say a plus m1t over the first half period and b plus m2t over the second half period. Thus a and b are just your intercepts. The m1 and m2 are your gradients, which can of course be positive or negative. Have a look in our problem here. Here the first one, the gradient is negative, and here the gradient is positive. What follows here is just a different way of writing this a plus m1t and b plus m2t. We can say, for instance, that m1 is given as v naught over half t naught, and m2 is given as w naught over half t naught. So if we say that, then of course v naught, so solving for v naught is just m1 t naught over 2. Now if you substitute for m1 and for t naught in here, in our problem, we will get minus 2. We'll explain now what that minus 2 means. And if you work out w naught, it is this m2 t naught over 2, and we found that w naught is 1. Take note, v naught is minus 2 and w naught is plus 1. Let's refer to the sketch over here. V naught is the slant height or depth, yeah, depending on when your gradient is positive or negative. If the gradient is negative in the first case, as you can see here, it goes down. And as you can see here, it has a value of minus 2. So it goes down by 2. Here, I think that is 2 there. And here, it is 0. So it goes down by 2. W naught we have calculated here is 1. So we expect to go up by 1. We expect it to go up by 1 W naught here. Over the positive, or let's rather say over the second half period, W naught, yeah, it is plus 1. You can see it starts from 2 and goes up to 3. It is positive, right? Since the gradient is positive. But that is not necessary to use this form, because our analysis in any case is going to be based on this form, the gradient intercept form. We first note, of course, that the a and the b, they may or may not be 0. So we start by calculating C naught. We split this up into two different integrals. The C naught here, as you can see here, there's your C naught over the full period. But we have to split it up over the two half periods. Why? Because we have two different straight lines. Over the first half period, we have a plus m1t. Over the second half period, we have b plus m2t. So substitute that in, work out it here, and Here's the general form of the answer. Yeah, in this line. And if we substitute for A and B and M1 and M2 and T naught, we get 7/4. The Cn likewise two definite integrals because of two different straight lines. The Cn, there's your general formula for the Cn. There you can see it. W of t e to the minus n omega naught t. We product that and we integrate. And here you can see it. So we have two definite integrals over the two half periods. First half period, second half period. A little bit complicated, but we can work it out. Here's your first definite integral over the first half period for a plus m1t e to the minus I n omega naught t. Work it out here. We use a integration by parts formula there, and we get this as the answer. Take note that the answer is given in terms of a, m1, and t naught. N that we see here is just the parameter in our formula for the Fourier series, n going here from minus infinity to plus infinity. So n basically is an integer there, or n represents the integers. Then we have the second definite integral here for the second straight line, and work out by integration by parts, and there's your answer. It is given in terms of b, m2, t naught, and n, where n is of course or is representative of the integers. N is also called the harmonic number if the waveform is periodic. So if n is equal to 1, we talk about the first harmonic. If n is equal to 2, we talk about the second harmonic. So there we have calculated C naught and Cn. So when we add up these two definite integrals here, or the answers to these two definite integrals, we get the Cn be equal to this. This is how we calculate the Cn. So there we have the answer for the Cn. So what remains now is to use the formula for the complex Fourier series, as you can see here. We filter out the C naught, and we say n is equal to plus minus 1 to plus minus infinity, Cn e to the I n omega naught. What is Cn? Yeah, we have calculated it. So there it is. So it's just a matter of substituting in here. This is your C naught, of course. The I, if we haven't mentioned this before, the I is the square root of minus 1, as you will already recognize from the complex form of the Fourier series. The I there happens to be the square root of minus 1. So we have then the Fourier series. Now that looks quite complicated. How do we sketch it? Now to sketch the Fourier series, we use the fact since the waveform is real, then the Cn is C minus n star as we have remarked above. So using this, we will eventually be able to write this form here in a different form. Starting here, the primitive form from minus to plus infinity Cn e to the I n omega naught t. Filter out C naught, so now we go from plus minus 1 to plus minus infinity. So we then have here n going from minus 1 to minus infinity here, and here n goes from plus 1 to plus infinity. But if we change this, and we say it's just a little bit of mathematical manipulation, so we take this over the positive integers, yeah, and then we just change the sign in front of the index n. Yeah, n here, minus n. The n there, minus. That remains, of course, the same. And as we have remarked here at the top, C minus n is Cn star. So we will therefore put Cn star there. Now you can see that both these summations go from 1 to infinity. So we can group them inside one summation from 1 to infinity. So there we have Cn and Cn star. So now we can substitute for Cn. There's your Cn, which we have calculated here at the top, right? Yeah, we just now look at the general form of the Cn. There it is. So we put it in here. There's your Cn. Then of course times e to the I omega naught t, e to the I omega naught t, plus Cn star. Now the only place where we see the I, or we see an I, is here. So we just change it to minus I for the complex conjugate. Now there you can see there's a minus for this I. The second term here is totally real. There is no I. So that means it remains the same there and there. So this can then be manipulated to these forms here, where we have e to the I n omega naught t minus e to the next I n omega naught t over 2I. Does this ring a bell? Yes, that is just the sign of n omega naught t using Euler's formula. And if we look at this form here, does it look familiar? That is just the cosine of n omega naught t, again Euler's formula, or related to Euler's formula. So instead of this, we will say sine, and instead of this, we will say cos. And the omega naught is just 2 pi over t naught, as we have remarked there right at the top. Omega naught, it is just 2 over t naught. So there is the general form of the Fourier series. Now we can therefore sketch this, and this is what we have done. Here we have sketched this up to the 10th harmonic. Obviously we cannot sketch up to the infinite harmonic, so we will have to be real. We sketch it up in this case here to the 10th harmonic. Now if we compare this graph with the one at the top, right, you see they pretty look not so different from one another, right? So this Fourier series up to the 10th harmonic is quite a good approximation to this periodic waveform over here. Okay, so obviously the more harmonics we use, the better approximation will be. So this is just your Fourier series here written out here at the bottom. Here we have plotted this up to the 10th harmonic. But if you want to plot it to, let's say, a different harmonic, like maybe the 5th harmonic or the 7th harmonic, or maybe the 12th harmonic or the 20th harmonic, what you can do is take this answer here for the Fourier series and create a function out of it, which we are going to do now. So we go to the top. Now that Fourier series, the answer there, right at the bottom, we have to put inside the memory. So here, that stands for memory in. Click on there, and if we go up, you can see there it is inside the memory. The memory is visible. Then we can clear this now, because while we have something inside the memory, we have an answer inside the memory, and create a function out of this. So we clear the screen because we have already explained this here, right to the bottom. So we will now create a function out of the Fourier series that you see right at the bottom, which is now inside the memory. All right, so we can now clear and plot this Fourier series up to a different harmonic. So clear the screen and clear some extra rows here in this calculator. There we close. There we close. Okay, so there we can even close that. So there is our alphabet. We can now create this function. Let's call it f. there. And now this function is going to be a function of two variables. Infinity, which we cannot use to plot, we will now take this as a variable. And the t, that is the time, that will be the other variable. So here we will have a function of two variables. Where's infinity? Here it is. So we click on there, that now becomes one variable. And we say, okay, comma, and t will be the other variable. So we say equal. Recall this now out of the memory, which is here, all right? This is just memory out, all right? Memory out, as you can see here, recall memory. Click on there, and there it is, all right? So we take this here to get an answer. Okay, the function is created, so let's just clear the screen. Okay, there you can see the function now. That's your Fourier series. So now we can, instead of infinity, obviously, we can now use a number. Let's say, and that number will then represent the harmonic number. So if we put in a 7 there, we will say we plot up to the 7th harmonic. We put in 10 there, we plot up to the 10th harmonic. If we put in 12 there, we plot up to the 12th harmonic. So here is 2D graphics, as you can see here at the bottom, 2D graphics. So click on there. We are ready now to plot. The time variable is here, the time variable. So we will say t going from, let's say, minus 8 to 8. And here we put in the function. If, okay, up to the 7th harmonic, up to the 9th harmonic, or up to the 15th harmonic. Obviously, the more harmonics, the longer it will take to plot. So let's say we plot up to the 7th harmonic. So we say comma, or 7 comma, there. As you can see, this is your function form. So we enter 7 here instead of infinity, obviously, because infinity is now a variable. And we enter t, which is t. So we plot from, this formula now goes from n equals 1 up to 7 when we plot this. So let's click here for an answer. And there it is. Here we have plotted this Fourier series up to the 7th harmonic. And that's it.